Hi, it's me again. To those of you in the group chat, I know that I said I would be doing this yesterday, and I'm really sorry I didn't get to that. The chapters took a lot longer than I thought I would. I was going to do it early this morning, but we went to go get our Christmas tree, so I didn't have time then either. So, sorry for the wait. I know it's sort of the final hour, but I do hope this helps you guys with the last year studying. I had someone ask me what the best way to study was, and I thought I would answer that question here because I think that everyone probably needs to hear this. And what I do when I'm studying for this course specifically, but most courses in general, is if it's a challenging course, what I do is I just sort of review everything, right? Like if there's a textbook, I'm reading through the textbook. And what you're doing while you're reading, though, is you're summarizing every little chapter up. That's what you're doing. So that's what these notes are, those PDFs in the description and whatnot. Those are my own summarizations of notes. Those aren't from when we started this class. I made those just for this final. And so you write down and you summarize everything as much as you can. And your goal during this is basically trying to understand the concepts. You're trying to understand why is force equal to mass times acceleration, right? Or in the case of our class, you would try to be figuring out like what is the difference between electric potential energy, electric potential, and potential difference. So that's your goal when you're summarizing these chapters, is to get the concepts down. And the really nice thing about that is that all those disgusting formulas and whatnot are based off of those concepts. I feel like one of the biggest problems in when we were taught this was that the math led the concepts. Mr. Yoner was using math to explain concepts, but instead, I think it's more effective in general to use concepts to explain the math. Like with Coulomb's law, which was the one about charge and whatnot, is the idea that, oh, okay, it's force is going down over distance, so you're dividing by distance, but it's also increasing by the size of the charge, so you're multiplying by that, and that's how you get force. So do that. Review everything, make summaries, understand the concepts. Once you understand the concepts and you have all your formulas and whatnot, you want to make a formula sheet. Get them all together in one little place. I have one right now, but it's a complete mess, and I have to really try and redo it basically. So I'm going to be doing that. But yeah, get your concepts, understand everything, and then make your formula sheet. And from there, just do practice tests. Practice test, practice test, practice test, practice test. I would say do like the practice final 3 times, and then look at the questions you missed each time, or take notes each time. And then, because our teacher was very kind enough to give us practice tests for each specific chapter, go through the chapters where you were messing up the most and see if you can, and practice with those. Do it a few times for each chapter you missed. Go back to the practice file. Do it again and again and again and again. Do it in class tomorrow until you have to take the final, which I actually can't remember if we have lab and class or if it's just lab or just class. So I'll look into that. But just practice test, practice test, practice test. And I think I talked about this in the group chat too. But yeah, that's how I would study, right? It's just those, 3 steps basically. Review, summarize, get everything together, and practice tests. So more like 4 tests, or 4 steps. Anyway, I looked at my last video painfully, and I noticed that despite my best efforts, I tended to get a bit off track still. I started talking about a lot of different things that I don't think completely related to what we needed it to at the moment. So I think that what I want the goal of this video to be is to give the basic concepts, right? Like last time, like I want to basically, every chapter that I go through is going to be another building block to help you guys understand what's going on. I think that's what I want this to be. So we're going to aim for that. And the notes, which is in the description of this video too, is going to be used as extra advancement, basically. It's more in-depth explanation than what I can give, because if I try to explain everything as in-depth as possible in this video, it'll be 2.5 hours, and no, I don't have that time, so we're not going to do that. But this will be for the basic concepts. The notes are going to be for basically understanding it more, and then practice tests are going to be you learning how to do that over and over. But anyway, without further ado, let's get started, right? So just a quick review from our last video. So to explain the story so far, in chapter 21, we figured out that there are basically two types of forces. There's positive and negative, or sorry, two types of charges. There's positive and negative charges. There's also particles that don't have a charge, which we call neutral charges. Then every charge or every particle has a force, and we use Coulomb's law to explain that force. And just like gravity is a force acting at a distance that diminishes the further away you get from it, it's the same thing with the electric force. And in the same way that gravity we show through gravitational fields, we use electric fields to show the forces from those charges. And that's what chapter 21 is talking about. It's talking about charges, the forces they can make, and it introduces the idea of electric field lines. And it also introduces the very big building block of law of conservation of charge, where you can't create charge, you can't destroy charge, you can only transfer it. You can only move it around or turn it into something else. That's how that works. Chapter 22 talks about Gauss's law and introduces the concept of electric flux, which is basically how many electric field lines are going through a certain amount of area. It's like basically the rate of change of force, or just how much force in a single area. Chapter 23 takes it up a notch and says, well, if we're conserving charge, that means we're conserving energy. So why don't we figure out how that's done? And they did. They figured out that there's basically three things you want to look at when it comes to electric energy. There's electric potential energy, which is just like real life potential energy. It's how much movement is possible at a certain position for an electron or a proton. Then you have, for the second thing, electric potential, which is basically the same thing as an electric field for forces, except this one is more like a field for potential energy. It tells you, oh, right, potential, the potential for potential, basically, is what that's telling you. And then you've got potential difference, which is basically the change or the difference between electric potential in one area and electric potential in the other. And a really good analogy for that is just that it's basically battery storage. It's literally how much energy you are capable of storing in this one place. And chapter 24 talks about that. It says that you use potential difference in things like batteries and capacitors. Those are things that store energy. Chapter 25 talks about how batteries use this potential difference as a way to make the charges move, and wires are used to conduct that through a path. And if it's connected to the terminals, you have a whole circuit. It talks about the ideas of current, which is the rate is basically charge over time. What is the flow of charge throughout the wire? And they talk about a resistance, which is the atoms of the particles colliding with each other, making it so that it's not completely as fast as it could be. That's called resistance. Then we use Ohm's law to basically talk about how voltage, which is another word for potential difference, is sort of just basically equal to current and resistance. And yeah, now we've got something called alternating current. So that's mostly chapter 24 stuff. And chapter 25 is basically picking up where we've left off, where we figured out that charges create forces, which means that there's energy, and we use that energy for electronics and to make charges move. That's the story so far, and we're going to pick it up in chapter 25. I've got my physical copy of this right here. And chapter 25, however, is basically the real start of circuits. So the way batteries work is that they create a potential difference. And in my notes, I talk about the exact chemical reactions that they do. And what you're basically left with, though, is a positive and a negative terminals of the battery. And there's a potential difference between those because, potential difference is basically just the movement of energy, but it's how much energy you get from that. So where there is a charge difference, there's potential for energy. So when it comes to something that's inside of a battery like that, they call that source EMF, which is basically just the voltage in a battery. So that's basically how batteries work, is they create a potential difference using electrodes and electrolytes. Electric current is, okay, so we didn't talk about this, so sorry for that last part, but basically electric current is the rate of charge over time. It's the same thing with velocity. Like velocity is position over time, current is charge over time. It's sort of the flow of current or flow of charge. Now, remember, charge can't be made or destroyed, only transferred. Light bulbs, things like that, don't absorb charge. They just use it as it flows. So they talk about that, and they come up with this very important law for circuits called Ohm's law, which basically says that the total voltage or potential difference for a circuit is equal to the current in that circuit times resistance. And resistance is something that is basically the collision that the electrons and protons have with the wire's own atoms, because they're going everywhere all at once, so there's going to be some resistance there. A quick clarification though, batteries don't give constant current. They give a constant voltage. That's very important, which, as we know, is going to be conserved because of our very first building block, law of conservation of charge. Always assume that things are going to be conserved in this course. That's sort of a baseline rule, in case that hasn't been made clear yet. But yeah, that's basically how it works. Current doesn't decrease or increase, it stays conserved. Same thing with voltage. Now, resistivity is 25-4. It's basically just something that comes with the material. We have a formula for resistance right there for if a question is asking about that. Electric power, they give you formulas for that. Talk about the power in household circuits. Really important thing they talk about, though, is alternating current. And what's really important about that is that this whole time we've been talking about, like, okay, voltage in a battery is constant, and the current that's going out is a steady current, right? Like, that's staying the same throughout. Maybe not because the battery is giving out constant current, it's because it's giving out constant voltage, which just happens to make the current stay like a constant steady rate. Alternating current is when you go from this to this. The current is now sinusoidal, which is where it's going up and down. It's ranging between two values. When a battery is connected to a circuit, the current moves steadily in one direction, which is known as DC current. There's also alternating current, which reverses many times per second, and sinusoidal in nature. They give basically a variety of different formulas about that. They talk about the waves and whatnot, the power, all of that stuff. And you might think, well, why would you want the current to be switching in direction and whatnot like that? Because actually, we're going to talk about this later. It'd be very important for things like magnetic fields and EM waves, which don't worry about that yet. Just know that AC currents for now are a thing, and you're going to need them later. But yeah, so that's chapter 25 right there. We now know that the reason why batteries use potential difference is to make charges move through a wire. And the rate of charge over time is known as current. Wires have resistance, which impedes that. And there's basically two types of current you can make. There's direct and alternating. And we use Ohm's law for direct current, and we use all the other wave stuff for alternating ones. Stuff like that. Chapter 26 gets a bit more into it. The first part talks about sort of how batteries have their own internal resistance, because that's how atoms work and whatnot. There's always going to be collisions that stop chemical processes from happening as efficiently as they could have. Talks about how, let's see, when current is first drawn, here we go. Yeah, so the voltage between terminals of that battery is called the EMF of the source. It's the potential difference, basically. And that's going to come up a lot later. Next part, they talk about resistors in series and parallel. This was something that confused me a lot, but I think my notes got it pretty well. If you want to figure out, like, basically just, there's different types of, so in series, right? Take a look at chapter 26-2 in this section of the notes. I drew out a little circuit here. For each resistance, there is a different voltage, and the reason we say that is because, well, current has to stay conserved because charge has to stay conserved. So current is the same for all of those, doesn't change. So that means that voltage and resistance are changing. And why are we saying that? Well, because we can't just assume that all the resistances are the same. So our baseline, our default idea is that, oh, each resistance is different, so that means voltage will be different for each one. It's sort of how that works. And so using V equals IR or Ohm's law, you can find out basically what the equivalent total voltage, current, and resistance of a circuit like that would be. Then you have parallel, which is the next page. That's basically going to, sorry, lost my train of thought there. The charges are basically going to split into different directions. And so now current is no longer the same throughout. Now it's voltage. And the reason why is because at point A, voltage there at point A is equal to the voltage in the battery. And because everything has to be conserved, the voltage at point B is also going to be the same at the voltage at the battery, which is the same as A, so on and so forth. So voltage is now the new constant. So voltage is the same for all three of those resistances and all three of those currents. That's why that makes sense and whatnot. And I even typed it out there because I had a really hard time figuring it out for a second. A really smart dude called Kirchhoff, he came up with two rules, the junction rule and the loop rule. Junction rule talks about how any current entering, like a junction or a split, the sum of the currents after have to equal the same. Basically, the amount of current going into a split path is the same as the currents going out. Loop rule is basically that, okay, based off of conservation of energy, the sum of changes in potential around a closed loop must be equal to 0. So potential difference is 0 because potential is conserved. Basically, just keep everything conserved is what he's saying. You can use that for loops and turn points. He talks about really quickly about EMFs in series and parallels. And then they talk about RC circuits and capacitor charging. So believe it or not, capacitors, you can use capacitors in circuits, of course, but they don't charge immediately, nor they discharge immediately, especially because, there's a source in there. And the notes talk about this, but the basic idea is that electrons are going from the negative terminal, and this is in 26-5, by the way. Electrons are going from the negative terminal into the capacitor plate, and that's leaving a positive charge on the lower plate. But that's actually starting to go against the normal current. And my battery's running out, so I'm going to pause the video really quickly. I'll be right back. And I'm back. Pretty quick, right? All right. Anyway, so as I was saying, right, electrons go from the negative terminal and leave a positive charge on the lower plate of that capacitor. But as more charge is added to that, we talked about this, the potential difference. Sorry, I basically pulled an all-nighter, but the potential difference is increasing, and that's going against the conventional current, because conventional current, as you remember, or as the notes talk about, I should say, conventional current starts on the positive terminal of the battery and goes to the negative terminal. And the reason why is because back when they were first doing all these cool calculations, they thought that positive charges were carrying the electricity and whatnot, but of course it's actually electrons. So they messed that up, and that's why positive charges are the standard for most things nowadays, because they thought those were the important ones, when in reality it's actually electrons. So that's why that happens, right? So basically, the longer that a circuit goes on, the longer a capacitor will continue to build up charge until at one point the potential difference inside the capacitor is going to equal the source potential difference from the battery, which basically means that there can't be any current flow because you have two opposing potential differences, and those are based on charges. So then you have currents, which are based off the rate of those charges. So you've got these two different rates, different but equal rates of charge going against each other, which means that there's no current happening on. So they describe this as capacitor charging. They use all these different formulas, use the notes for that. They also talk about how you would discharge that. So now we've covered chapters 25 and 26. We know about circuits. We know how to talk about the voltage in them, which is the potential difference from the battery. We know how to define current, which is the rate of charge over time in that battery. And we can figure out what resistance is, which is based off of the material of the wire. So we know all that. We also know Kirchhoff's rule. We know how capacitors work and all that, etc., etc. Now we are going to take a detour. And I'm going to warn you guys that these next couple of chapters are what I would consider to be the hardest ones. I think that the hardest chapter in this whole book to understand is chapter 30. Chapter 30 is, for anyone who has just finished reviewing, you will know that that is a tough cookie to understand. There's a lot of things going on in there, but we're going to try and do this one thing at a time, chapter by chapter. We're now on chapter 27, so that's happening. But you're probably asking, okay, why? What's new? What are we doing to the electricity? Nothing yet. We're actually going to talk about magnets now. We're taking a bit of a detour. It's gonna come back. It'll loop all back around into this one crazy thing. But for right now, we need to talk about magnets, and that's what chapter 27 does. It talks about just the nature of magnets, right? And it talks about how that there is no such thing as a magnetic monopole. And what that is basically just like, what is it possible to have just a positive magnet or just a negative magnet? Kind of like electrons and protons work. The answer is no. The thing with magnets is that there's always a positive and a negative part, or a north and a south. The north pole of a magnet is pointing towards geographic north, by the way, which funnily enough would make our south pole of the Earth, our Earth's south pole, that would actually make it a magnetic north pole because it's pointing towards the north pole. That sounded terrible. Go look at a picture of it. It's actually a cute little factoid there. But yeah, so you can basically treat magnets, so you can't treat magnets quite like electric charges, but what we can say is that, hey, they still have magnetic fields, right? And you can treat those a lot like electric charges. Those go from, if I remember correctly, they basically point from the south pole to the north pole is how that goes. So negative to positive, I think. Yeah, that's how it works. Okay, so they talk about magnets for a while, but they come across these really smart fucker scientists, which is their patent pending name. They come up with this really cool realization that, hey, currents, like the currents in our wires that we were just talking about, the rate of charge over time, that's creating magnetic fields. Magnetic fields produced by current in a straight wire are in the shape of a circle with the wire at the center. And you're going to use this thing called the right-hand rule a lot for figuring out direction. Magnitude, you just figure out through math, but direction, you need to use your actual hand to do that. And I don't know how to do that. I'm actually having to relearn that now, and I haven't had time. So I'll leave you guys to figure that out. But yeah, that's basically what's happening right now. Chapter is basically just that we figured out that currents are creating a magnetic field, and which basically implies that there's a force there because, magnets are carrying forces on each other. So it's assumed that magnetic fields are doing some type of force, which means that currents are doing a force on them. So if 27-3, if electric currents are exerting forces on magnets, then they figured that the reverse is true also, that magnetic fields are also exerting a force on current. And so they talk about that. They talk about how force is perpendicular to both the direction of current in an electric wire and also the direction of the magnetic field. Pretty cool stuff, but just remember the basic idea is that, hey, our electricity is making magnetic fields now, and that's pretty baller ass if I say so. Pardon my Spanish there, but that's basically what's happening. 27-4, they try and figure out, like, oh, what is the force on just a singular charge like that, right? Which they talk about. I'm not going to spend too much time on it. They also discuss what torque is, talk about the discovery of the electron, the Hall effect, which is pretty cool, I think, but I talk about it in the notes, so just look at that. I think I did a pretty good job explaining it. So, anyway, chapter 27 is basically just the introduction to magnets and the new building block that, hey, those electric currents that we found out in the last chapter, yeah, those are creating magnets now, which is pretty cool. Chapter 28 is basically discovering the relationship between the magnetic field, the current, the electric field, all that. They figure out that for a straight wire, they say, oh, okay, well, the magnetic field is obviously getting stronger the higher the current is. So B is going to just be directly proportional to I. B is magnetic field, I is current. But it's going to get smaller over distance, so that's going to be R. So divided by R. So B is equal to this constant mu naught over 2 pi times the current over the distance. That's all that's saying right there. That's all that first equation is saying. That a magnetic field is directly proportional, that it increases with current and decreases with distance. That's how that works. So they then think about like, okay, well, hey, these are obviously exerting some type of force. What happens if you put two of them together? They figure that out and whatnot. They also talk about the definition of ampere and the Coulomb, and they talk about Ampere's law. And this is one of the more important equations you're going to find. The earlier equation, the one I just talked to you guys about, is only valid for a long straight wire, which if you guys have ever seen a circuit board, you know that it's not just a bunch of long straight wires. There are all these little curves and turns and paths and whatnot. And it would be really tedious to just do every single one of those paths at once, even though you could if you wanted to, but it would take a while and just there's all sorts of different things. So we want something more general, right? That's where this smart dude Ampere comes in. He imagines that there is a closed path around with a wire inside of it. And he's saying like, well, okay, we know that basically if it's like every little distance L of that path is going to have some type of magnetic field in it. And it would be the magnetic field parallel to it, just because that's how the math works out. So what if we just add all those up together? We know that the magnetic field is directly related to current and distance. Since we're already taking care of distance, that means it's just pretty much related to current, isn't it? So he figured that out. He said that, okay, the first equation here in 28-4 all it's saying is the total sum of the magnetic field times the distances is equal to the current inside of that whole area, which he then put into that next form there, which is saying that, hey, the area within this total length of wire with this magnetic field is equal to the current inside of it times the constant mu naught. That's all that's saying. It's saying, okay, hey, all this magnetic field in this area is just equal to that. And it works. That's how the math works. It's really good for figuring that sort of stuff out. But in the same way that Gauss's law can be used for anything, but it only makes sense to use it with symmetry. It's the same thing with Ampere's law here, because trying to take the integral of a square is easy, but trying to take the integral of like a freaking, I don't know, something like this, just imagine this, but 2D or something, that's going to be way harder. So we don't use it for stuff like that generally. But they think about, oh, hey, this is still an amazing step. We just figured out how to relate the magnetic field to the current, and we can do that for pretty much any shape we want now. Like, what? How cool are we? So they start inventing a bunch of whole other things. They invent this thing called a solenoid, which is a long coil of wire with many loops, basically. And each of those loops, and I basically diagrammed it there, but they start messing around with stuff like that. They look at the magnetic fields there. But as I just said, there's still a lot of restrictions with Ampere's law, mainly just that it only really works best and works simply when there's symmetry. So like, what the hell do we do about some wonky donkey wires? Like, what do we do there? Enter these two other smart boys, certified smart boys, Biot and Savart. These two guys basically said that a current could be imagined as a whole bunch of tiny current elements, and that every single one of those tiny current elements has a tiny little length that goes with it. So they do all this crazy wonky math, and they come up with that starred equation that you're going to see there. And this is now equation section 26-8, by the way. And more simply, the second equation is dB equals mu naught over 4 pi times I dl sine theta over r squared. And theta is the angle between dl and r. What the fuck does that mean? That was like hieroglyphics right there. I'm pretty sure you need a history language degree to even understand half of that. Like, this is a crazy complicated formula. When I first saw it, I wanted to throw up, but it's actually a lot simpler than it looks. So I'm going to explain it like this, right? So it's really hard to figure out the total magnetic field over a total length of an area. Like, that's just hard to do. So what if instead we just say that, like, oh, let's just look at a tiny, tiny little magnet field. That's what dB is. dB is a tiny little magnet field. Well, wherever there's a tiny magnetic field, there's going to be that tiny little length that you're basing it off of. So that's what dB and dl are. And so as it's sort of based off of, nah, that's not what I mean. Sorry, but just dB is tiny magnet field, dl is tiny length. Mu over 4 pi is just another constant. I is the current, and r is basically the distance between the wire that you're looking at, the wire which has that dl, that's where that little length is, it's wire, and you're looking at the distance between that wire and a point where you want to measure the magnetic field. That r is the distance between that, and angle is, and theta is the angle between the length and the distance away or something. It's like right here, like that. All this equation is saying is that a tiny magnetic field depends on the current, the length of the wire, the tiny length of the wire, and the distance between the wire and your point, and the angle between them. And that's it. And the really cool thing about this is that this works for everything. It's not just for straight wires. It's not just best used for symmetry. This works for any kind of shape of wire you can imagine at any distance away. So they start doing more crazy things. They think about things like magnetic dipole fields. They talk about single charges, which they realize is a paradox. They start experimenting with ferromagnets like iron, which iron is not magnetic, but it has domains, is what we call it, little regions that are magnetic, that align very nicely with magnetic fields. And they use those for creating these really powerful magnetic fields through like solenoids and whatnot. They put iron inside of that solenoid shape, which is a bunch of coils of wire, and that just creates all these huge magnetic fields. And they're doing all these magnetic fields in materials. They find out about hysteresis, paramagnetism, diamagnetism. They're fucking tripping balls at this point. They're like, bro, magnets. Like, magnets is like their new thing. It's like the Pogs of the 90s, but for physicists. They're like, yo, magnets? I'm in. You kidding me? And so they're just having a blast, right? So 27 was us just figuring out what magnets were and their nature. Chapter 28 was us realizing just how integral they are when it comes to electricity and how you can relate those. Because of smart, certified motherfuckers like Ampere, Biot, and Savart doing friggin' cool-ass mathematics. I wish I had my sunglasses on at this point to give that extra... Oh, hold on. Alright. They're doing certified cool guy math at this point. Now we're in chapter 29. I'm such a moron. Now we're in chapter 29, and there's this other certified smart dude called Faraday. And Faraday's like, okay, so hold on now. You're telling me that magnets create currents, right? Like fucking that's crazy, right? And so actually no, specifically he was like, what we just found out was that, oh, hang on, so this moving current inside this wire, this changing current is creating magnetic fields. That's super cool, but what if the opposite is true? That's the question that he was asking. He was saying, what if it's possible that a moving magnetic field or a changing magnetic field was inducing an electric current? Long story short, he was right. The reverse was also true, and they call that induced current, or EMF, which is confusing because earlier we said that EMF was equal to like the voltage in a battery, right? So why are you like, is EMF current or is it voltage? And the answer is dependent on context. If you're talking about batteries, it's voltage. If you're talking about magnets and currents, then it's current. And the reason why is basically because of Ohm's law, right? Voltage is directly related to current. And what a changing magnetic field is doing, and this is the next bullet point, when the magnetic field in a coil is changing, a current occurs in there as if there was a source of EMF in the current in the circuit. So that's why it's called EMF or induced current, even though it's confusing and stupid, or maybe I don't understand it right, and if I don't, I'm sorry. I'm trying my best, but yeah, that's why they call it that. It's super weird and confusing, and it kind of throws people off, but it's also called EMF, is the induced current thanks to a changing magnetic field. So, we talked about that for a while, and this guy Faraday, he's like, okay, he puts his cool guy glasses back on, right? And he says that, okay, well, the EMF induced, right? That's gotta be, and he leans back as far as he can when he's saying this, because he doesn't care what Newton says about gravity. He owns gravity at this point. He's not gonna fall on his ass. He's Faraday. Faraday is like, the EMF induced is proportional to the rate of change of the flux, right? And flux, by the way, is, I don't know if I even mentioned this for electricity, but magnetic flux is basically the amount of magnetic field per area. So that exists for magnets too, right? And it's also true for electricity. And so he figures out like, okay, he figures out like how to define flux, right? He's like flexing his smartness right now. He's like, okay, this is what the flux is, and the EMF induced is equal to the negative rate of change of this, which is like, kind of makes sense because it's talking about, because, how do I say it, right? So an induced current is equal to the rate of change of the magnetic flux. Magnetic flux is equal to the magnetic field over an area. We know that the area probably isn't changing of the wires, right? So that means that the magnetic field is changing. Well, we just said earlier that a changing magnetic field is inducing that current. So that's basically what this is saying, is that, hey, this current is happening because the magnetic field is changing. Is basically what that starred one there is saying, that E equals negative d flux B over dt. That's all that's saying, is that magnets, that changing fields create induced currents inside of circuits. Now, be aware that there is, at this point, this is a huge point to get down. There are two different magnetic fields at this point. The first one was the moving magnetic field that produced that current, or that induced that current. Now, there's the magnetic field that current is producing, because remember, we found out in chapter 28 that moving currents, are making magnetic fields. So it's sort of like a ping pong table match between just like who is creating the next magnetic field, where they are just never dropping the ball and they're creating all these really weird things. And of course, they're going in opposite directions though, because you can kind of visualize that too. So the two different magnetic fields are actually going to be directly opposing each other. And that's valid even in open circuits, actually. And I don't really know how to explain that, so I'm not going to. Even I have my limits. Anyway, so Now this guy Faraday is like, he takes off his glasses at this point. He's like, fuck this shit. Are you kidding me? We just figured out that like moving currents make magnet fields, and moving magnet fields make currents. We can do so much with this, and they do. They figure out about uh, EMF induced in like more moving currents or more moving areas and whatnot. They figure out about electric generators, like AC generators. They use the idea of EMF, which is basically magnets turning, or yeah, currents making magnets and magnets making currents, just to create mechanical energy. They do that. They find out about things like back EMF, counter torque, eddy currents, which I'm not talking about. That's a lot of stuff. And then they talk about transformers and the transmission of power, all this really cool stuff. They talk about how they make the slight little note that like, oh, hey, because currents are moving currents have an electric field, something I think I talked about no, we haven't talked about this yet actually, but basically currents have an electric field, and the reason why is because currents are just the rate of charge over time, and we established that, hey, moving charges have an electric field, so therefore currents are creating electric fields. So this is just, they also talk about that as like, hey, technically this change in magnetic flux is actually making electric fields too. So that's what they're saying there. And they're going on a field day at this point, right? They're like, dude, we're converting magnets into electricity into magnets, and we're getting mechanical energy out of all this. There's a lot of stuff happening, and like, we're all super happy, you know? And so that's what they're talking about, right? Now, I'm going to warn you guys, this video has been going on for a long time already, and if this hasn't helped you at all, I am so sorry. But I'm going to warn you guys now that these next two chapters, chapters 30 and 31, are easily... No, chapter 30, this chapter right here. 31 you can handle, but chapter 30 in particular, I think is the worst chapter in this book. It is where everything we've taken so far is going to get cranked to the max. Like, it's to the point that even I barely understand it. And I mean, I barely understand a lot of things, but I feel like I've learned enough at this point here to be able to tell you guys about it. But chapter 30 is just a giant fuck you from physics. So we're going to go through it. I'm not going to be able to explain everything. I'm going to explain things as best I can, though, and I hope that helps. But just know that if you're confused on this, that's totally okay. If you can even get a little bit better in this area, that's great. If you actually understand chapter 30 and chapter 29 and whatnot and all that stuff, you are in amazing shape. Just start doing your practice tests, you know? Anyway, without further ado, let's get into chapter 30. So let's review really quickly, right? We know that potential difference in a battery, which we call source EMF, that creates a current throughout the circuit, and that current is also related to resistance, and all three are related to each other. And you can put those circuits into like parallel and series and whatnot. You can do funny stuff with capacitors, all that really cool stuff. You put that in with magnets though, and you have a lot of new realizations, like that magnets have magnetic fields, that moving currents create those magnetic fields or induce magnetic fields, and that magnetic or moving magnetic fields induce currents. By the way, important note just to say, but I've been saying create a lot, but I hope I've also said just as many times conservation of charge, right? So when I say create, I hope you know that for me it's just easier to say create, but it's more, a better word to use would be like induce or something. So just remember that. But yeah, so we know how circuits work. We know about just all these sorts of stuff. We know that magnets can induce electric charges, and electric charges or electric currents, and electric currents can induce magnetic fields. We figured out the general relationship between those two. We also figured out with Faraday's law and whatnot that, you know, it is reversible like that, that there's two different types of magnetic fields at this point, where, like a magnetic field, a moving one is creating a moving current, and a moving current is then creating more magnetic field, and they're opposing each other. Everything is sort of starting to come together now. And now we're at chapter 30, this beast here, and they talk about something called mutual inductance. Imagine two coils of wires are near each other, and that there is a moving or changing current in one of them. That changing current is going to induce a current in the other. Why? Because that changing current in that first wire is creating or inducing magnetic fields. Those magnetic fields go certain distances, so they're going to start creating currents in the other one, and those are going to start creating fields back and whatnot. So now you have two of those back and forth systems going next to each other now, but they're also impacting each other. So we found out, we're calling this mutual inductance, where the wires are inducing currents on each other. And Faraday and other really smart scientists were able to find out that, got an itch in my mouth, sorry, but they were able to find out how the EMF, the induced current, is equal to basically just like the change in current and the mutual inductance and all of that. They also found out that the mutual inductance in one coil is equal to the mutual inductance in the other coil. So really important thing, it helps simplify the formulas down a lot. But they realized that, like, okay, cool, so that kind of makes sense, right? That whole process of currents creating fields, creating currents in the other one, which is creating fields, which is creating currents in the other one. It's like, okay, that's a lot of extra steps, but it makes sense, right? Like, that's the only way that you would be able to get a charge like that, is because they're doing it to each other. That's basically the end of inductance, right? Nope, you can also have the wires do it to themselves, which is a very, very fun and fascinating and theoretically amazing idea, but it's so fucking complicated. So the concept of inductance, and I wrote this down, concept of inductance also applies to a single isolated coil of N turns. When a changing current passes through a coil, a changing magnetic flux, which remember is just magnetic field over area, a changing flux is produced, and that induces an EMF, or a current, inside of itself, which opposes its original current and diminishes its increase. So in this case, self-inductance is actually, for the most part, a bad thing. It's creating backlash on the other current. And normally this is very, very small, yes, but it still exists, and we're still going to get tested on it, of course, is the other thing. But it's small, but it's still hindering things. So we say that self-inductance is represented by the letter L, and that's equal to the number of loops times that magnetic field, and it's over I, because the higher that the current is, the less impact that it will have on it overall. But if you have like a really small current, like just 1 or 2 amps, or milliamps even, like that's going to have an even bigger effect. So stuff like that. Blah, blah, blah. AC currents always have some inductance. So this is where those alternating current circuits, where the current was sinusoidal, going between maximum and minimum values, it's always going to have some conductance, and again, some inductance. It's usually very small, but it's still there. Now, a coil with a significant amount of inductance is called an inductor. And again, I wrote it down here, more nuisance than help. It disrupts the current flow. You can negate inductance, funnily enough, by just having the coils go back on each other like that, because it sort of just cancels it out. Not entirely, of course, but to a much better extent, which I think is pretty funny. You're basically creating a problem and solving it, so yeah. Anyway, so now we're probably asking, like, okay, so not only can we induce charges or currents on each other, but we're also inducing it on ourselves. That's making the idea of energy seem even more crazy now. Like, is there a way that we could define energy in all this? And the answer is yes. For an inductor. So when an inductor with inductance L is carrying a current that is changing at a certain rate, power is supplied by the current times the EMF, which is referring to, I think, the source voltage. So basically, power is equal to the inductance times the current times the change in the current. And work done to increase the current from 0 to I is done there. So do all this stuff to figure out what the potential energy is and what energy density is inside of a inductor. So they figure that out. And now they're thinking about how, like, okay, well, this is actually like a whole new thing now, right? Like in the same way that like capacitors was sort of impacting the whole point of the circuit, this is going to do that too. So we have a bunch of new circuits now, like LR and LRC circuits. LR circuits are circuits with inductors and resistance. LRC circuits are all the above: inductors, resistance, and capacitors. And sorry, there's an intermediate step in there, more like an ideal, called the LC circuit. And I'm just going to let you guys read that part because it's mostly just math. And I think the parts that aren't math I explained pretty well, so I'll just let you guys read that. So we're just going to skip that. But we have basically a new type of resistance now. Here comes a new challenger. It's a resistance that's we are going to call reactance, and it's based off of, there's a reactance for capacitors and there's a reactance for inductors. And this happens during those alternating current things right there. So this is just for those. Again, more math, but when an alternating current source for resistors, right, we'll just take a quick look. When an alternating current source is connected to a resistor, the current increases and decreases with an alternating voltage. And they basically use Ohm's law to try and figure that out. And that's basically just the same for all of it. I'm just reading my own notes here just to make sure I'm not missing anything I need to. Oh, here we go. Right, so inductors, capacitors, and resistors are all out of phase, which means that basically the maximum amount of current in one of these things is not going to be the maximum amount of current in the other thing at the same time. Like they will reach the same maxes most likely, but it'll be at different times. So you'll have something like, if this is current in maybe the inductor and this is current in the capacitor, like this is at its max, this is at its minimum, it's going to be like that because again it's sinusoidal. And that's same for voltage as well. So not everything's in phase, so you need to account for that. I talk about that too. You can tell I want to cry just talking about this. It's such a nightmare, but we're almost done, I promise. They really quickly talk about LRC series, AC circuits, phasor diagrams. They talk about total impedance, which is basically like resistance, but now it's also including the ideas of inductors and capacitors. And they talk about that too, so I'm going to just let them do that. Resonance in AC circuits, which alternating current circuits, when it's sinusoidal, that's for when that happens. When that happens, that is going to have the reactances of the inductor and the capacitor actually be matching. So that's what's happening there. And on that note, we are done with chapter 30. I don't think I did a very good job explaining that, and I apologize, but that's honestly the best way I can even explain it to myself as someone who hasn't really done practice tests for that one yet. So if that didn't help at all, if that was really confusing, I'm really sorry. That's the best way I can describe it though. So I would recommend going through the book, going online, and doing practice tests for this. At the very least, like, you have the concepts and ideas done now, even if you don't understand all the logic behind it. You know what each variable can mean now, and because I talk about it in the notes. So just cross-reference. I think that should help you guys a lot, even if this explanation didn't. But anyway, we are now up to we have 2 chapters left. And honestly, we've made it through the worst part. It's still a lot, but this is so much easier. Chapter 31. We're going to go back to, this is at the point where the physicists who were writing this book realized that, like, oh shoot, man, this last season was terrible. People miss the cool guy scientists, so they fucking brought him back, right? So you've got all these amazing new laws. You've got Ampere's law, Faraday's law. You've got things like Gauss's and whatnot, and these are all great and dandy, but they sort of belong in their own world, right? Like Gauss's is for electricity. You've got Faraday's, which is mostly just like it compares the two, but like it's only for like specific circumstances. Then comes along the biggest brain scientist yet. His name was Maxwell, and he basically figured out that, like, oh, the cycle between magnets and electricity just repeats itself. If a changing magnetic field can produce an electric field, which, again, remember, the reason why that works is because changing magnetic fields create currents. Currents have charges that are moving, which means that there's an electric field. So he was like, okay, if a magnetic field can produce an electric field, maybe a changing electric field could produce a magnetic field. And he found that out. And what he basically theorized and concluded was that, hey, if we take a look at the electric field in between the plates of a capacitor, that would actually be equal to an electric current. And that electric field is also changing. And you're probably thinking, like, why is the electric field changing in between capacitor plates? It's because charge itself is not, I mean, it's changing. Yeah, like the concentration and whatnot. Like charges are moving, like the concentrations are changing. So that means that electric field has to kind of be changing too. And he basically said, well, that has to be equal to a current. And he called that current the displacement current, which is a terrible name for it. It has nothing to do with anything it talks about, but he basically said that, like, okay, let's say that this changing electric field, right? And he got his cool guy swag on. He's like, let's say that this changing electric field is equal to this current, which found out was right. But using this idea, he was able to generalize everything. He was able to generalize Ampere's law, Gauss's laws. He was able to get Faraday's too, everything. And this is chapter 31-3, Maxwell's equations. He summarizes everything, right? He's got Gauss's law for electricity. He's got Gauss's law for magnetism. He's got Faraday's law. He's got Ampere's law. Everything is as general as it could possibly be. And they are quite literally as fundamental to electricity and magnetism as Newton's 3 laws are to our normal world. Like, holy shit. This is basically just big brain just taking over the whole room. He just makes everything make sense. And I talk about that in the notes. But anyway, so he's like, he does all that and he's still not satisfied, right? He's like, okay, well, shoot, man. So now we know that a changing electric field will create a magnetic field, and a changing magnetic field will create an electric field. But more importantly on the first part, right? Changing electric fields do stuff to magnets, which, I mean, like, kind of makes sense because we've been seeing them being able to be reversed like that for a while now, so makes sense, right? Well, now he's going to start thinking really hard, right? And he's like, well, what happens if you do this sort of process in, like, empty space, right? Like what if you did something like that where, like, there's like almost no charges or anything? Well, he found out that a electric or a magnetic field would be produced in an empty space if there is a changing electric field. And he realized that this process repeats itself. He realized that if a changing electric field produces a magnetic field, well, that means that magnetic field is probably going to start changing too. That changing magnetic field will create an electric field. That electric field is going to start changing, and then it's going to go on and on and on and on and on. And he found that the net result of all these different fields changing each other was that they ended up creating a wave made up of electric and magnetic fields that traveled through all of space. And you can take a look at this in my notes. I talk about the ideas that they go in, which is like closing a switch and whatnot, but the most important thing he realized that, and this is why alternating current is so important. This is what it's been building up to. This is why we cared about the magnetic and electric fields that were being made, is because when you do this experiment with alternating voltage, instead of just, oh, little waves go out a little distance and then they take forever to get further, these ones make like pulsating waves, like and they're like compounding. They're going out, and they're basically keeping themselves going. They keep on reinforcing themselves, building each other up. And I talk about graphs in this and whatnot. They change sinusoidally. You can sort of see all that. These are known as electromagnetic waves. And in 31-5, he uses all his equations as if they were in empty space and whatnot, as in where there are no charges. And he realized the very important realization that, well, the velocity of this wave is equal to the electric field over the magnetic field. And that speed just happens to be equal to a little number called 3 times 10 to the 8 meters a second. As in the fucking speed of light. These tiny little fields of magnets and electricity, they're going the speed of light. Just because they can. And they're not running out anytime soon. They're just helping each other. That's crazy. Like, that's crazy how much they're doing that. So then he realizes, like, well, hold on, right? These things are going the sort of speed of light. This is just helping prove even more how much light just acts like a wave. And so then they come up with the idea of the wavelength spectrum, right? Like what do you call it? But it's like, the spectrum of light, basically. Visible, infrared, gamma, X-ray, radio. They come up with all of that. They realize that these are all different EM waves with their own frequencies and wavelengths. They figure out what the energy density is in that, how much energy they would have over time. And they figure out, and they come up with this new thing called intensity, which is basically just, It's basically just that it's the average intensity over time. And intensity, by the way, is equal to the amount of energy over time. So the unit is basically just like, it's the amount of energy over time over area. And it's the average of that. It's weird, but read the notes. It should make a bit more sense. And he finds out about radiation pressure, which is like, okay, well, hold on. We've seen many times before that these fields have forces. What's the force there? He figures that out. He figures out what the pressure that they're causing is. He basically figures out just the ultimate fusion, the ultimate Dragon Ball Z fusion of electric and magnetic. And he just was able to come up with this light spectrum. He was able to figure out the force that those things cause. Everything. It's the reason, like, it's just radiation pressure, everything, just all from that. And thus concludes sort of the magnet saga. We have one more chapter left, but it's not related at all. It actually comes after 17 through 20, which is the kinetic energy and the gas molecule stuff, but I don't have time to cover that, so I won't. But anyway, we have covered so much. A lot, actually. Over an hour's worth of stuff, and I really hope it's helped. But here's the story so far, right? Because the whole point of this was to try and tell a story, starting from the very beginning, right? We know that particles have charges. We know that those charges create forces, and where there's force, there's energy. We figured out how to measure that energy and store it in batteries with capacitors and voltage differences and whatnot. And we knew how to make that charge from that potential difference flow through a conducting wire. We made resistors, and we figured out current and resistance and all that stuff. We figured out that those moving currents create magnetic fields. We figured out that moving magnetic fields create currents, that electricity and magnetism are just that intertwined. We figured out these incredible formulas. We made waves of electricity and magnetism that just go the speed of light. They just permeate everything. we basically figured out the microscopic world in that sense, at least in terms of just that, but it's as fundamental to our world as is F equals ma. And they did it. They did it very complicatedly, but they did it. And as painful as it is to try and learn all of it, it's also kind of incredibly beautiful when you take a step back to realize like what was actually accomplished, because that's easy to lose when you learn about this. And so now we have one final chapter left that I'm going to review, and I'm going to do practice tests as an all-nighter, because why not? And we're basically going to stick to the theme of, well, hey, we've come this far, let's go as far as we can. We've figured out about particles and everything. We're going to go to basically the quantum realm. That's what chapter 37 is. Chapter 37 is the quantum mechanics chapter. Now, we start this final chapter, the sort of DLC packet, with a question that scientists were not able to answer for a really long time, which was, hey, what is the relationship between light and temperature? Because sometimes when things get really hot, light it's glowing, it's luminous, and for other things it just sets on fire. Like, what is the relationship between light and temperature? What can we find out? How does it differ by material? They couldn't figure this out for a really long time, but they sort of came up, the first step they did was to come up with something called a black body, which is a terrible name, but it's basically an object that can absorb, how does it work? It's an object that can absorb all radiation of light falling on it. And the radiation that that body would emit when hot and luminous, it's called black body radiation. And so they basically figured out that, like, okay, so using this sort of ideal, we can see that the wavelength at that peak intensity, which again is the it's the energy over area over time, which is in that last chapter, chapter 31. That's where they talk about in there. And that's known as Wien's law. And, you know, this was nice, but like this is a good step is to like defining like what a relationship could be, but we still don't know how the hell to explain that until smart boy Planck came along, and he was like, hey, here's a crazy idea, right? What if we say that the smallest amount of energy, right, like the energy of the vibrations of just atoms existing, it's not continuous. It's not like 1, 1.1, 1.2, etc. There's actually like a minimum amount, and every form of energy emanating from that is like a multiple of that. So that's where you get that equation E equals NHF. It's the Planck length times the frequency times basically the number of vibrations, if I remember correctly. And so therefore there's actually a minimal amount of energy that you can have in this world, and that is HF. 1 times HF. It's the quantum of energy. It's as small as you can get. That's why absolute zero can't exist, because according to absolute zero, there is no energy, but there's always some energy, and this is as low as it goes, which is fucking insane. When everyone heard that, they were like, oh, so energy isn't like continuous? What does this mean? But, you know, at first, even Planck at the time was like, you know, hey, it's just a theory. I don't think it's that, like, it's not meant to be groundbreaking. But then Einstein came around with the biggest fucking brain in the whole room, making everyone else's brains look like freaking silver dollars compared to his South African diamond. And he's like, well, hold on now. You're onto something there, Planck. Einstein argued that when light is emitted by a molecular oscillator, the energy has to decrease by HF, and he figured out that E equals HF for light. Basically figured out the photoelectric effect. The important stuff is that there's another type of particle out there called a photon. And photon is basically light energy. It's light particles. And it like upon collision with like an electron, they just disappear and vanish. The electron gets all of their energy, all that ridiculous stuff. He comes up with these equations relating the total energy to kinetic and the work done. Talks about how the loosest electrons will get the most kinetic energy, all this stuff. But basically, photon electric theory has three predictions: that an increase in the intensity of light means that more photons are created, so more electrons are ejected. But energy of each photon can't change because it's as small as it can be. So neither so since those energies aren't changing, neither's the kinetic energy of the possible kinetic energy of electrons. Figures out that like if the frequency of light is increasing, then yeah, the kinetic energy will increase. If the frequency is less than the cutoff to eject electrons, then nothing's going to get ejected. He determines the energy, mass, momentum of these photons. He realizes that they have zero mass, and any mass that they do have is pure energy, which is insane. That basically means that they are moving around at all times. And the reason why that works is because, potential energy is based off of mass and gravity. So since they're never moving, that means that they have no potential energy, which means that they have no mass, basically enough. So he figures out all that. He figures out the Compton effect, which basically is just proving what Einstein was saying. They talk about photon interactions and all this just to say that, like, well, hang on now, wait a minute. Like, we are so crazy far ahead. We think that light is a wave, but you're talking about photons, like light particles. So is light a wave, or is it just a stream of particles? The answer is yes. Light is both a wave and a particle based on the scenario. Some experiments show it's a wave, some show it's a particle, and they call this the wave-particle duality. And Niels Bohr loved this. He was like, oh, they complement each other. It's like the two halves, basically. So they figure out sort of like the wave nature of matter in general, sort of how much that works. They make all these electron microscopes. They talk about atomic spectra, the Bohr model, stuff like that. They talk about the correspondence principle, but basically just, yeah, light is a wave and a particle. Energy is not continuous. Mass can be made purely out of energy. And if God hadn't taken a seventh day off, maybe none of this shit would have happened. Is basically what we found out. So that's it. That's pretty much everything. The PDF in the description. I meant to mention this at the beginning, but I just completely forgot. For some reason, and I couldn't get it to work. But it's in reverse, so start from the bottom, go from the top. But that's it. That's everything about this. I'm not doing 17 through 20 because I don't have time, but I really hope this helped you guys out, and if it didn't, I'm sorry, but yeah, at the very least I know I can explain most of the things, except for inductance. You saw me during that chapter. I can't explain that, but yeah. Anyway, good luck on your test. Make sure you understand so my 4 steps are: make sure you understand the concepts, review everything, which is what my notes do, and these videos do. Make a formula sheet, and just do practice test. And that's it. And as one final piece of advice, just know that just because you failed doesn't mean you're a failure. You're allowed to fuck things up. As long as you're trying to go the distance, I think that's all that really matters. So no matter what happens, no matter how good or bad you think you'll do, go the distance. And don't do it because I'm telling you to or because the teacher's telling you to. Do it for yourself. But on that note, I leave you all goodbye. I don't really know how to say goodbye, so bye. And hope this helps.